All right, I think we should actually start now. So welcome everyone to the CNM short course on using AI/ML for modeling and characterization of nanoscale materials that is organized by Maria Chan, Henry Chan, and myself. I'm Subramanian Shankar Narayanan, group leader for the theory and modeling at the Center for Nanoscale Materials. And today I will actually start off with a brief overview of what the theory group is and what our capabilities are, which you will actually hear more about from the theory staff and theory members, group members. All right, so the theory and modeling group currently has 5 scientific staff and one support staff who's basically our system admin. So the scientific staff are Maria Chan, Stephen Gray, Pierre Derance, Henry Chan, and myself. And Michael Sternberg is our system administrator who also manages the computing cluster that we have here at the CNM called Carbon. And he will actually talk more about the capabilities that Carbon offers and how it is a useful resource for everyone who's actually interested in AI/ML. We have also around 15 postdocs and 20 students and a named fellow as part of the theory group. We also have Benoit Roux, a faculty at U Chicago, who's a joint appointment, and I myself have a joint appointment with the University of Illinois, Chicago. So that's our staffing. The vision of the theory group and our goal is to actually provide theory and modeling so that we can actually understand and predict energy and information processes in nanoscale systems. And our focus is, of course, on certain strategic scientific themes here at the CNM. And those themes actually are now being updated. The AI/ML is a strategic theme in itself for our division, as well as for our directorate and DOE in general. It is an area that is growing as we speak. The CNM's distinguishing strength is that the theory staff members have significant breadth and depth across different modeling and simulation techniques that range from first principles theory and quantum dynamics to atomistic and coarse-grained modeling. We develop algorithms and workflows in areas such as quantum information and sensing, and our AI/ML efforts specifically are focused on multi-fidelity scale bridging and multidimensional inverse problems. And you will hear from the theory group members today on this particular topic on scale bridging, solving inverse problems, and how it can be applied to modeling and characterization of nanoscale materials. So there are also other experimental groups within the Center for Nanoscale Materials, and the theory group actually actively collaborates with many of these groups that are actually present both within the CNM as well as in other divisions and directorates at Argonne. All right, so one of the distinguishing capability that we have is our computing cluster Carbon, which is like a 3,000 core and now 44 GPUs. It's a high performance computing cluster, hosts numerous electronic structure, molecular dynamics, and continuum dynamics softwares, mostly open source codes, as well as codes that are actually developed by the theory group, some of which are actually listed here, and you will hear more about them later as part of this short course. So we are in the process of upgrading nodes in the coming few years with more AI/ML friendly processors. So this is an important step that we are actually taking to cater to our users who basically want to do AI/ML in designing and discovering nanoscale materials. We also work with our users, and depending on the scale of the problem, we actually provide them and work with them to give them access to the ALCF resources, including Cerebras, which is a deep learning accelerator, as well as exascale computing resources that are now coming up, such as Aurora. So in terms of the scientific questions, what we are interested in are some of these questions, such as where are the atoms? So can we incorporate simulation into real-time experiments to inform and direct the discovery characterization process? We are interested in what do these atoms do? So can we make reliable prediction of materials with specific properties? And finally, we are interested in how do we actually put them in places where we want them to be. So this basically caters to the synthesis aspect, and we are like I said, working closely with our experimental collaborators, looking at some of these synthesis pathways, such as self and directed assembly, interfacial processes, and so on, that are relevant to achieving the desired materials. So within the theory and modeling group, what we do is that we try to answer these big questions within program in data science for materials discovery and characterization. So these are kind of highlighted here: integrated imaging, multi-fidelity modeling, AI-guided inverse design, and autonomous synthesis. So if we want to actually put our efforts in AI for nanoscale materials in chemistry, there are three broad areas that we are actually interested in. The first one is what we call as predict. So we want to actually make predictions. We want to develop models and simulate everything from atoms to devices. And so one of the areas where AI/ML is used is to actually bridge the gap between these different modeling and simulation techniques. And in this respect, we actually develop physics-aware, both informed and constrained, flexible models. So that is all in the bucket of making predictions. The next big area that we actually focus on is interpretation, and you will hear more about that in the afternoon. So the idea here is to overcome the spatio-temporal resolution limits of various experimental probes, whether it is X-ray imaging or electron microscopy and so on, or spectroscopy. And the idea here is to, of course, do high-throughput calculations that allow for, combined with AI/ML, that allow for better interpretation and control of these spatio-temporal probes. And if you can actually make predictions, if you can have better interpretation, you can go ahead and then synthesize these materials. And so within these, we actually focus on certain aspects, such as, looking at closed loop synthesis. And Henry Chan is actually going to talk about our autonomous synthesis platforms and how we are actually kind of enabling autonomous synthesis for polymers, for example. And then the other area that is of interest for us within this synthesis is to actually look at materials beyond equilibrium. So in this respect, we are actually both looking at the thermodynamics as well as the kinetics of how do we identify pathways for reliable synthesis of metastable materials. And so that's an active area of research for us. So today, what you will basically hear is from Michael Sternberg on the carbon computing cluster, and then you will hear from Aditya Koniru on a BLAST framework, which is basically one of the frameworks for multi-fidelity scale bridging. And then later on in the morning, you will actually hear from Subo Banik, who will talk about the casting framework for inverse structure design and processing microstructure optimization. We will break and have a question and answer session, followed by sessions that focus on synthesis. So Henry is going to talk about POLYBOT, and then Joshua, Chaitanya, and Katerina are going to talk about various different characterization, like AI/ML characterization tools that are being developed by Maria Chan's group. So that will be basically, finally, we will have a session on question and answers related to all of these different topics that we will cover today. With that, I would like to thank you all. You must have seen a link for user survey that was posted by Henry Chan. You must have also received an email from Maria Chan. Please fill out this user survey. This is very important to us. And that's all. From my end, if you have questions, please feel free to drop in the chat or ask. And then we will basically start now with Michael telling us about our carbon computing cluster. Thank you.
Good morning, everyone. working with multiple monitors is always a bit of an adventure. Okay, here we are. Thank you, Subu, for the nice introduction. So my task is to briefly describe what we have in terms of HPC computing in-house. Subu already alluded to some of the other resources that CNM users would be able to access. As far as Common is concerned, here we go. Our cluster has been architected from the get-go for nanoscience, modeling, and simulation. And we also have capabilities for real-time data processing. So for some folks with experimental background, this will be of increasing importance in the next few years. Here's how this looks in practice, our system. So when this was designed in 2007, this was a transition from the early Beowulf type computing clusters that you saw in the early 2000s. Yeah, we switched to rack-mounted systems pretty soon. The system is located in the building of CNM in our data center there. We currently have 8 racks and cooling included. And here are some numbers for the physical characteristics as far as power consumption is concerned, and well, airflow. Yours truly sitting there on the right, out of the floor is some cold air coming up at like 15 degrees C, and then in the back of these racks, it's about 40 degrees C, so nice and balmy. But most of you won't really ever see this with remote access. So what you will see is the system software and the application software. Sorry, let's first, go to, to actually access the